This is a third example of work. These are going to be involved with pumping liquid in or out of a tank. And I'm going to do a specific example and talk about some different things as we go through this example. So it says a spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. It says find the work required to pump oil out through a hole in the top of the tank. Now first of all, you got to keep in mind whether you're trying to pump the liquid in or out. That's going to make a huge difference as far as your bounds are set up when you integrate, and we'll get there in just a minute and talk about that. Also, you need to keep in mind whether you're trying to pump it in from the bottom, or you're trying to pump it in from the top, or you're trying to pump it out. So you have to keep some different things in mind as you're going through this, and that's just going to change the way you set up different expressions algebraically in there as you go through the problem here. So in this case, we go back to our basic definition of work, which is force times distance. Now, I have a sphere, so what I'm going to do is I'm going to take a slice of this sphere. So when I take the slice of that sphere, that's going to give me the force, because basically when I'm looking at the force, I'm just looking at a weight of one of these slices. Now, this tank is half full of oil, so there I am, half full of oil, and then I'm going to take a slice through here. In this case, I just drew it in red there. And since this is a sphere, when I take a slice out of that, I'm going to get a disc. So if I'm going to find the weight of that disc, the weight of that disc is going to be its volume, which in this case is going to be the area of a circle times the height, so pi r squared times the height. And then to get the entire weight, I need the density, which in this case they told me the density of oil is 50 pounds per cubic foot. Now the other thing I'm going to need is I'm going to need the distance, but we'll get to the distance in just a second as we're talking through this. Alright, now a couple of things in this case. In this case, I have a sphere. Now I usually, when I set these up, I put the ground level as the x-axis. You can set them up however you want, but to me, to stay consistent, I usually set them all up with the ground level being the x-axis. You don't have to do it that way. There's many different ways you can set these up, but that's just the way I'm going to do them in general. Alright, so we're working on a slice of the disc. Now again, this tank in this case is already half full of oil, and we're going to try to pump this oil out through the top of that tank. So we're going to figure out how much work it's going to take to move that oil, all that oil up and out of that tank. Alright, so it's half full. So what I'm going to do is I'm going to take basically this sphere in 2 dimensions, which would be a circle. And so I need my radius of this slice here. So the distance the radius, is just here in red, that length there, and that length there is just some x value. So to figure out what that x value is, which is basically going to give me my radius, I need a formula for that circle that you see right there in 2 dimensions. So what I did is I centered that circle right on the y-axis with it touching on the x-axis, so my center of that circle is at 0, 8. So I can get the equation of a circle. So the equation of my circle here is that x squared plus y minus 8 squared is equal to my radius, which is 8 squared, which is going to be 64. So that's just the formula for my circle in general. So at any level, so my slice that I have here, this slice that I have here, at any level, I want to find out what that corresponding x value is. Well, I can use the equation that I have right there for that circle to help me find that value for x there. So if I move this y minus 8 squared over to the other side, I get that x squared is equal to 64 minus, and then I have y minus 8 squared there. Back over here in my formula, I need my radius squared, which basically, for what I'm looking at over here, is just x squared. So this formula is pi times x squared times my height, which we'll talk about, times 50. Alright, so these are equal signs over here. Let me draw a line through there so you won't get confused with my equal signs. Sorry about that. So I'm going to rewrite x squared over here in this equation. So I'm going to do a little bit of simplifying. So x squared is going to be equal to 64 minus, and then I'm going to multiply out that binomial there. So that's going to be y squared minus 16y and then plus 64. So x squared is going to be equal to 64 minus y squared plus 16y and then minus 64. And so when I do that, let me get a little bit more room down here. So when I do that, I get that x squared is equal to 16y minus y squared. So back over here in my formula, what I have now is I now know that my work is pi times my radius squared, which I just found to be 16y minus y squared, times the height. So let's talk about the height for just a second. This disk, how big or how little of a slice I make is up to me. Now they're horizontal, so they're going to be stacked one on top of each other. So the height of this little disc that I take is just how thick or thin of a slice I take, which basically is just going to be my change in y, or delta y. So 16y minus y squared is my radius squared times my height, which is I'm calling delta y, times 50. And all that I'm going to multiply by my distance. Alright, so this is what we have so far. We've got our weight of a slice, and we'll deal with the delta y in just a second when we put this into the integral. That'll turn into my dy. Now I need to figure out my distance, which basically is how far I'm going to move it. Alright, well this slice, my picture is going to get a little ugly here, so bear with me. But this slice that I take is up here at some distance y from the ground. Some y value, and y is ranging from 0 to 8, so keep that in mind as well, because y is going from 0 to 8 because my tank was half full of oil. The distance I need to move it is out from the top. So the distance that I need to move that at any point in time here, all the way to the top, is 16, and the distance I'm going to have to move it is 16 minus wherever my water level is at. And again, remember, my water level is varying from my oil level is varying from 0 all the way to 8. So the distance that I'm going to need to move it is 16 minus y. So that's what I need to put in down there. So every single time with these pumping problems, you've got to consider all those different things, whether you're pumping it in, whether you're pumping it out. If you already have liquid in there, where you're pumping it from, where you're pumping it out, whether you're pumping it out the top or in from the top, like I said, or in from the bottom. So keep all those things in mind when you set these up, because that's going to change your expressions that you have there. Alright, now this force is not constant, so we need some integration here. So my work is going to be the integral. Now remember, we just said that our oil level is going from 0 to 8 because we're half full. So I'm going to go from 0 to 8 of the weight, which we found to be pi times 16y minus y squared times 50. And we'll put the delta y at the end, that's my dy, times, and then my distance that we're going to move it is 16 minus y, and all that is dy or delta y. So there's my formula that I'm going to use to integrate here to find the work done. Alright, so my work is going to be equal to, again, this is not the hard part. The hard part we did all the hard part, which is setting it up. So keep that in mind. So 50 pi is a constant, so I'm going to pull out the 50 pi. So this is 50 pi times the integral from 0 to 8 of 16y minus y squared, all that times 16 minus y, all that dy. So if we multiply that out and combine like terms in there, this is what you're going to get if you multiply that out and combine the like terms. So integral from 0 to 8, you're going to get 256y minus 32y squared, and then plus y to the third, all that dy. And then, as always, you're going to want to integrate each one of those pieces. And so these are just have constants in front of them, powers of y. So if we integrate this, we get the work is equal to 50 pi times, this is going to become 128y squared, minus, and this is going to become 32 over 3 times y to the third, plus, and this is going to become 1/4 y to the fourth. All that evaluated from 0 to 8. Now it's nice at 0 because everything turns into 0. So if you plug in 8 everywhere you see, multiply all that, simplify it, what you get is that the work is, and I'm rounding here, is approximately 589,782 foot-pounds is the work done. Again, I'll let you plug in the 8 and just pull out your calculator and simplify that. That's the easiest way to deal with that. But that's not the hard part. The hard part was up at the top. So I want to go back and talk about that again just for a second. So every single time you have these pumping problems, you have to find these two pieces. You've got to find the weight of that slice that you take. And again, it's going to depend on the shape. In this case, it was a sphere, so I just looked at it in 2 dimensions, and in 2 dimensions it was going to be a circle. And I just centered it on the y-axis where it touched at ground level so that my center was at 0.8, and that made things work out pretty nice for me. But your slice in 2 dimensions could be a square, could be a rectangle, could be a triangle, could be any kind of shape. So keep that in mind. And you need to find the weight of that slice, which basically means you're going to have to find the volume of that slice and multiply it by the density of whatever your liquid happens to be. So that's going to be extremely important. That's the first piece that you need. And then the other piece is the distance that you're going to move that liquid. Whether you're pumping it in, whether you're pumping it out, that's where you're going to have to keep in mind whether you're trying to pump it out the top, whether you're trying to pump it out the bottom, or you're trying to pump it in from the bottom, or you're trying to pump it in from the top. That's what's going to change this formula over here for distance, is depending upon those things. And then in this case, since I already had some liquid in the tank, my values for my integration bounds varied from 0 to 8 since it was half full. But again, those bounds would change depending on whether you were trying to, whether it already was liquid in the tank or you were trying to pump the liquid in. That would change those bounds. So those are the 3 most important pieces that you have for this problem. Is you got to find the weight of that slice, and then the distance is going to depend on some different things, and then your integration bounds. Those 3 pieces are the most difficult part of these problems. And you're going to have to draw you a picture, and like I said, how you draw your picture is going to change your equations as well. I mean, there's more than one way to draw this. I just happen to draw it this way, but there are different ways you can draw it, so that's going to change your setup as well. So keep that in mind, that just because you set it up one way and some other person sets it up a different way, neither one of you may be incorrect. It just depends on how you're setting it up. So keep all those different things in mind. I hope this one example will help you with the other examples you have in your homework. And that's the last example for work.